All right. Hello, everybody. So, obviously, I'm not here today, so we're going to run through your notes today, which is actually pretty similar to what we looked at yesterday, or in this case, Friday. And it's just now we have some context here that we're going to be playing with as opposed to just generic numbers. Okay. So, what we're going to do here, read through this, figure out what's going on, break it down. So the heights of fully grown white oak trees are normally distributed. All right, that's pretty key. Remember, that's one of our characteristics we're looking for to tell us that we can use that central limit theorem. So if it's normally distributed, sample size doesn't matter anymore. So, all right, we got a mean of 90 feet. That is your mu. Standard deviation of 3.5. That is right in there, is your sigma there, your standard deviation. Following graph already put together for us. Lovely. Random samples of size 4 are drawn from the population, and the mean of each sample is determined. Okay, so doing our entire setup here on the central limit theorem. Find the mean and standard error of the mean of the sampling distribution, then sketch the graph of the sampling distribution. So, all right, so remember the mean of the sampling distribution, which is mu x bar, is going to be the same as that population mean. So no calculations really going on here. It's just 90, in this case 90 feet. You're going to be specific. Okay. All right. Your standard error from your sample, that's your sigma x bar. That's where we have to do our standard deviation, that 3.5, and divide it by the square root of our sample size. So the sample size is 4, so that's just 3.5 divided by the square root of 4, which is 2. Which gives you an overall answer then of 1.75. Okay. So that's it for the mean and standard error. Then we need to sketch our little graph here where we need those 3 points. So I'm going to keep this scale the same as I do this. So I'm going to go from 80, 85, 90, 95, 100. All right. Then my highest point is going to be at that mean, so I'm going to put a high point here at 90. How high you put it doesn't really matter as long as it's the highest one on there, so I'm going to just throw it on there. And then I want 3 standard errors either way. So this is 1 standard error, so 3 standard errors. It's going to be taking that and multiplying by 3, right? So we have 1.75 times 3. So let me grab my calculator here. 1.75 times 3 gives us 5.25. And that's what the distance we're going to travel overall in either direction. So I'm going to subtract it to go left and add it to go right from that 90. So 90 plus 5.25 is going to take us to 95.25. So just barely past that 95 mark. And then 90 minus 5.25 is going to be 84.75, so just past that 85 mark as well. So fit that in there. Ooh, missed a little bit. Going through there. And you got your graph. You're good. Cool. All right, that's example 1. Example 2, flipping down here. So the consumption of processed fruits by people in the U.S. in the recent year was normally distributed. Golden, already normally distributed. Mean of 152.7, standard deviation of 51.6. Random samples of size 35 are drawn from the population. Use the central limit theorem to find the mean, standard error of the mean of the sampling distribution, and then sketch the graph. Basically the exact same setup there. Sorry, I just realized I was a little high. So just running through here, you can read it. Not a big deal. Okay, so sample mean, as always, it's the exact same as our normal mean, so still at 152.7. And then our standard error is our standard deviation, 51.6, divided by the square root of our sample size of 35, which should take us to 8.72. Okay. Sketching our graph. This one doesn't have a graph, so we can pick our own scale. The easiest way to do this is to put your mean right in the middle since I don't have a scale yet. And then just go by your standard deviations. Okay? Sorry, pointed the wrong thing. Your actual standard deviation, that 51.6. And then we'll graph the standard error, but use the standard deviation down here. So I'm going to add that 51.6 and then subtract 51.6 depending on which direction we're going. So that'll take us to, let's see, 204.3 and 255.9. And then subtracting will be 101.1 and 49.5. So just taking that mean right in the middle, then adding 51.6, adding 51.6, and then subtracting 51.6, subtracting 51.6. Okay. That way it lines up really nicely as we go through here. All right, so high point on the mean, 3 of our standard errors. It will take us to 8.72 times 3, 26.16. So I'm going to add that to our 152.7 and then subtract to get a point on each side, which is 178.86 when I add that on there. So that's going to be right about here. All right, and then subtracting 152.7 minus 26.6 would take us to 126.54, which will be right about there. All right. Put your graph in, being careful not to run into that x-axis, and we're good to go. All right, one left. Try to line it up so you can see it this time. All right. Mean age of employees of a large corporation is 52.4 years, standard deviation of 4.1. Random sample sizes of size 30 are drawn from the population, and the mean of each sample is determined. Notice it does not say anywhere that is normally distributed. That means I have to be careful. So in this case, I do have samples of size 30, so I'm good to go. But if it was any smaller, since it's not normally distributed, if it was size 25, 20, even 29, no go. We can't do the central limit theorem. So make sure you keep an eye on that. All right. Mean still matches. So mean age is 52.4. And our standard error is going to be 4.1 divided by our square root of 30, which comes out to 0.75-ish. You know, always rounding these a little bit. All right. So picking our our scale, same thing. Put that mean right in the middle, and then you're going to go by that population standard deviation. That 4.1 there is going to be how I'm going left and right. So I'm going to add 4.1, which takes me to 56.5 and 60.6. And then subtracting to go left will take me to 48.3 and 44.2. Okay. All right, so high point on the mean. 3 of these takes us to, forgot to write those down ahead of time, 2.25. I couldn't figure that out. Anyway, 2.25, so 54.65 when I add here, so that'll be 2, or right about there. And then subtracting will take us to 50.15, which is about right in the middle there. Connect them together, trying to get that bell curve as nicely as we can, and you're all set. There you go. So each of these, we found our mean of our sampling distribution, the standard error in our sampling distribution, and then sketched our distribution.